Welcome to Lubitex Engineering, where we sketch out the things that keep the industrial world moving. Now, let's start.
All right, today we're going to unpack one of the most powerful, yet honestly, most overlooked pieces of machinery in the entire modern world. I'm talking about the industrial gearbox. No, seriously, these things are the absolute unsung heroes of manufacturing. They're what drive the conveyors, turn those massive mixers, and power the crushers that make, well, pretty much everything we use, wear, and eat. They are everywhere, just working silently behind the scenes. Which begs the question, right? For a machine that's so fundamental, what does it actually do? Because, it's not just some random box of gears. It's a master of physics, really. And it's designed to do one single, absolutely crucial thing. And that is the whole magic trick right there. Think about an electric motor. It spins incredibly fast, right? But with relatively little force. A gearbox, well, it takes that high-speed, low-force input and completely flips it. It converts it into a slow, deliberate, but immensely powerful output. That's how you get the raw muscle needed to move like mountains of material. Okay, so how does it actually do that? Well, to understand it, we've got to look inside, check out its core components, and talk about the one thing this machine is built from the ground up to create: torque. Think about using a wrench on a really stubborn bolt. The longer the handle, the more leverage you have. That's torque. A gearbox is basically just a really, really efficient mechanical lever. It takes that fast spin from the motor and just multiplies that rotational force, that torque, to do all the heavy lifting. And this image, wow, it just illustrates the principle perfectly. So check this out. That small gear, that's called the pinion, it's hooked up to the motor and it's spinning super fast. As its teeth mesh with that big gear, it forces the big one to turn, but way, way more slowly. And because that large gear has a much bigger lever arm, so to speak, the rotational force is just magnified. Speed plummets, but power just skyrocket. Now you might think a gear is just a gear, right? But nope. The actual shape of the teeth is an absolutely critical design choice. It's this constant engineering balancing act between simplicity, strength, and just how smoothly it all runs. So on one hand, you've got what are called spur gears. Their teeth are perfectly straight. Super simple, cheap to make. But when the teeth connect, the entire face just slams into place all at once. It's this clack sound. That creates a ton of shock and noise, which means you can really only use them for lower speeds. Then you've got helical gears. See how their teeth are cut at an angle? This means they engage gradually, nice and smooth. They're way quieter and can handle up to 50% more load. But there's always a but, right? The catch is that angle actually pushes the gears sideways. This creates a force called axial thrust. And let me tell you, that will absolutely destroy standard bearings. So this was a massive engineering problem, right? You want all that smooth power you get from angled teeth, but you've got to find a way to cancel out that destructive sideways push. And the solution? It's just beautifully simple. It's just pure genius. You literally take one helical gear that's pushing to the left, and you stick another one right next to it that's a perfect mirror image pushing to the right. And boom, the two opposing forces just cancel each other out perfectly. And this simple idea gives birth to two very similar, but also very distinct gear designs. Okay, so the whole difference here comes down to a tiny little space, or lack of one, between the two halves. A herringbone gear has zero gap, none. This makes it super compact, but it's incredibly difficult and expensive to manufacture. You need very specialized tools. The double helical gear, on the other hand, has a small relief gap or channel cut between the two sides. And that little gap makes all the difference because it lets standard gear cutting tools get in there and do the job. So it's much easier and cheaper to make, even if it takes up a little more room. All right, so far we've been talking about all these elegant designs and really precise engineering. But you have to remember, these machines operate under just immense, immense stress. And when that precision starts to break down, well, the consequences can be incredibly severe. Yeah, all of that torque, all of that power, the very thing that's so useful when it's controlled, it can become an instrument of its own destruction. I mean, just look at this. This isn't just a little bit of wear and tear. This is a catastrophic failure. The surfaces of these gear teeth have been completely shredded. And when a gearbox fails like this, it doesn't just, quietly stop working. No, it can seize up an entire production line, costing a company tens, sometimes even hundreds of thousands of dollars for every single hour it's down. So, what causes something this bad? Well, if you look at the data here, you'll see something pretty surprising. Yeah, things like overloading and misuse are big factors for sure, but they're not the biggest problem. Just look at that huge slice of the pie: lubrication failure. A staggering 41% of failures come down to a problem with the oil. And when you add in that 10% from contamination, you realize that over half of all these catastrophic failures happen just because the oil is wrong, or it's dirty, or it's simply not there. And this right here brings us to maybe the most important part of this whole story. Because if we know what causes these failures, well, that means we also know how to prevent them. In fact, get this, according to maintenance experts, a full 70%, 70, of all gearbox failures are preventable. Completely preventable with just routine scheduled inspections and proper care. It's not about luck, it's all about process. So how do you prevent it? It really just boils down to a clear plan focused on 4 critical zones. Number 1, and this is the big one, the oil and lubrication. Check the level, the condition, the temperature. Number 2, vibration and noise. Is the machine humming along, or is it starting to click, whine, or grind? Those are your earliest warning signs. Number 3, alignment and mounting. This is the silent killer of bearings. You've got to verify the shaft alignment. And finally, number 4, the seals and housings. They're the gatekeepers, keeping contamination out. You got to inspect for leaks and blockages. And this quote from a principal reliability engineer, man, it just sums it all up perfectly. A $30 oil sample sent to a lab monthly can save you a $30,000 unplanned replacement. I mean, the return on investment for preventative maintenance is just astronomical. Think about that. $30 to potentially save $30,000? So if you walk away with nothing else today, what are the top 3 early warning signs you absolutely have to watch for? First, abnormally high oil temperature. If that thing is running over 80 degrees Celsius or about 176 Fahrenheit, something is definitely wrong. Second, rising vibration readings. Even tiny changes are a huge red flag. And third, and this is a big one, check what you find on the magnetic drain plug. If you pull it out and see shiny flakes or little chunks of metal, you've got a very serious problem brewing inside that box. You know, the gearbox itself is all about a trade-off, right? It trades speed for incredible power. So that leaves one final question, especially for anyone who manages these machines. Are you making the right trade-off? By skipping a simple oil check or ignoring a strange new noise, are you trading the short-term convenience of just keeping things running for the near certainty of a catastrophic and way more costly long-term failure? It's definitely something to think about.
Thanks for watching. For more industrial insights, check out our other videos. Don't forget to like, share, and subscribe to Lubitex Engineering.